So the course will be in English. I'm not sure for everyone to understand, and also it will be recorded. So then I hope to upload it on YouTube so that it could be understandable for everyone. So welcome to this introductory course to, as you can read here, but maybe not on the video, quantum foundations and quantum information. So I'm currently a postdoc at Vienna University in Czeslaw Bruckner's group. My work mainly focuses on broadly quantum foundations, but I have a lot of interest also in fundamental aspects of quantum field theory, quantum gravity in the long term, and in fact, every possible problem there exists in physics. I can have some interest in it. So I'm just a PhD plus 1 year. So, so first, this is a selection of topics that I'm really, confident with. There are plenty of other topics that I could have selected, talked about, but I chose to well, first what I think is scientifically most important, but also what I'm most confident with. So I'm PhD plus 1 year. So please, so you can ask as many questions as you wish, whenever you wish. So just raise your hand. I like when it's interactive, but be prepared that I might answer, I don't know, from time to time, because I'm not a well-established professor. So I chose a quite unconventional presentation. So what you will have, it really doesn't look like what you can have in basic textbooks, introductory to quantum foundations. I really made it quite personal. So for example, I will not talk about quantum computing, the theory of quantum communications, many topics that can exist in quantum information. I will also not talk about quantum reference frame, very fashionable at the moment in quantum foundation, but because I'm not expert enough in this. But you can ask questions, and I might know a few details if you want. I will try to be provocative. So I'm here in CPT, so many people are doing quantum gravity, high energy physics, quantum field theory, field theories in general. So I will try to provoke a bit, sometimes show or try to argue that some basic quantum mechanics questions can be extremely relevant for more high energy physics fields. And sometimes even that the approach that we have in quantum foundation can even be more promising. But when I'm provocative like this, don't take it literally. I'm here also to receive some feedback and some criticism, and I'm really ready to change my mind all the time. So I also wanted to do a little game at mid part of every session, like a little enigma, little puzzle. To brief a bit and change our mind and do something else, but I have so much to say. It's crazy. Only for the first 2 chapters, I have already the 25 pages of notes. So what I will do is propose the puzzle at the end of the session, and then you have 1 week to think about it, and we can discuss it at the beginning of, so that we lose less time at the beginning of the next section. If I forget, please remind me to give the enigma in the end. And last thing, so as you saw in the invitation email, my name is Antoine Soulas, but in any informal context, I have a preferred name, kind of nickname if you want, which is Shoops. So please call me Shoops if you like, and if you can. So this is the summary. So 3 references. So the first one is not a reference to read. Don't read it, but it's of historical huge importance, and so I will very often refer to it, but mostly because of the huge influence it had on the development of quantum mechanics. But don't read it. If you want to read one, read this one. It's really cool. It's Asher Perez, so from the Israel school. So you can, if you want to, just have a look at it. You can ask me. It's in my office for the whole month. So it's quite rigorous, and a lot of topics are investigated, and sometimes topics that you don't find in other textbooks. And it's very operational, very empirically based. So I love his style. But there are dozens of other good books, so it's almost impossible to do a list. But so for mathematicians or mathematical physicists, I would recommend the last one. It's wonderful. So 𝗦𝘂𝗺𝗿𝘆 is a Swedish guy, and Karol J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J.J. Bengtsson, he loves beautiful math, beautiful geometry, and he's able to show you how quantum mechanics is a very deep geometrical theory. He's rigorous, exhaustive. I love this book. If you want to spend some good time reading beautiful geometry, read the third one. So this is the summary. So detailed summary for today, and I don't know where I will stop today. First, so I wanted to do a short chapter on basics of quantum mechanics so that everyone starts with the same knowledge. So because there is no prerequisites, as I said in the invitation. I wanted it to be short, and then when writing it, of course, I wanted to explain many things that are almost never explained in the textbooks or never rigorously as I think. So in fact, it became much longer, but you will see there will be a lot of content, already a lot of possible debates, even some references to what we do in QFT and so on. So I hope you will not be get bored at all. I think you will not get bored in the first chapter. Second chapter will be much more philosophical about the measurement problem. So the textbooks in general, they put the measurement problem at the very end. It's, you know, when you have done a lot of very serious math, you can maybe keep 5 minutes to think about what quantum mechanics means about reality. But for me, it's one of the most important things. So after having settled the basis, I focus on that, because then it will give a flavor to all the rest. Chapter 4 will be about important no-go theorem. The most famous of all will be Bell theorem, of course, but I will present two other less famous, but very significant as well. Chapter 4, theory of decoherence. So I worked a lot in this during my PhD thesis. It's unavoidable if you want to really understand quantum mechanics, to understand what is decoherence. It's not an additional theory, it's just a consequence of quantum theory, which is not so hard, but it's unavoidable when you really want to understand. And then you use it everywhere. And chapter 5, which maybe, yeah, extremely important to my mind. Scientifically, I think it's one of the greatest challenges in quantum physics, possibly in physics. A century-old problem, which is how to recover, if you believe that quantum mechanics is universal and fundamental, how come our world appears so different? Where does the Newtonian physics come from? Still unsettled debate. So I will present selected topics on this, because every day you find, you know, papers on the archive released on this problem. And the very last part of this chapter will be a bit of an advertisement, where I will present some well, my research program for the following years. Good. So let's go for chapter 1 and Dirac's notation. So Dirac's notation, it's really like Einstein's notation. So literally every quantum physicist use them. And once you have, you know, wired your brain to think in this notation, you just cannot help using them and cannot think anymore in another notation, system of notation. But I'm sure you all know very well, but just very short recap. So first, so everything takes place in a Hilbert space, separable Hilbert space. This you know very well. In a separable Hilbert space, denoted H, calligraphic H. We associate a separable Hilbert space to every quantum system under study. And so what are the Dirac notations? So first, for vectors in H, will be denoted this way, generally psi or other letters, but in this notation, and this is called a ket. And then, because it's a Hilbert space, you have Reed's theorem, and so to every vector you can associate uniquely a linear form. And so this will be the linear form, or maybe psi, linear form associated to this vector in the dual Hilbert space. And we call this a bra. And why this? Of course, because then when we want to take the scalar product, which is a complex, it's a complex Hilbert space. So scalar product is a complex number, and so we call this a bracket. Right, and then there's no specific word for this, but there is still the notation. When you want to take a rank 1 projector, linear operator, so this lives in the linear operators of H. Rank 1 projector, it's a matrix element if you want. There's no word, but you can denote it this way, and so you understand very well what it means. Not necessarily. No, you can take two vectors, and so this is the linear operator, which you feed it with phi, and it outputs psi. Good. So enough for Dirac's notation. Let's go to the most important thing of quantum mechanics, which is to compute. Sorry, no, it's not a projector. It's a rank 1 operator. Sorry, yeah. Thank you. So computing probabilities. And first, this will be the PVM presentation. I will explain what this means. So this is the most important thing you want to do with quantum theory, because quantum theory is just physics. So what you want to do is make predictions about experiments. How do you compute probabilities in quantum theory? So here's the punchline that I will repeat many times and sometimes change it a little bit. QM for quantum mechanics, is a geometrical way to compute probabilities. Okay, this is the punchline, which will be a bit extended further in the next chapter. But for now, let's start with this. So how do you compute probabilities? So first, physical states of a system correspond mathematically to unit vectors so unit vectors they live in the unit complex sphere of H, right? So unit sphere, one sphere. So the physical state are elements of the sphere. Then it's a probability theory. So what you want is compute the probabilities of events. So what are the probabilistic events? They correspond to subspaces, linear subspaces F in H. Events are subspaces. And how do you compute the probability now of an event, given that you are in a state, physical state? So you use the so-called Born rule, because Max Born kind of pioneered this idea of the probabilistic interpretation of the quantum state. Long story. We'll come back to this. What is the Born rule? Probability when you are in state psi of an event F is given by a wonderfully elegant formula. You just take the square norm of the orthogonal projector on the subspace of the the state side, right? Orthogonal projector. You cannot imagine more elegant, more refined, and in particular, if F is one-dimensional, so it's C times some vector phi, one-dimensional events. Well, the Born rule gives P of psi. Well, I should write, yeah, C times. It becomes just the scalar product, the modulus square of the scalar product. So honestly, I couldn't imagine more elegant. And the crazy thing is that every experiment that humans have done in quantum labs since the advent of the theory, so since century, perfectly agree with this wonderfully beautiful formula. Now, we also want, so what is the mathematical object associated to a complete set of incompatible events? So complete set incompatible events. For example, would be the outcome of a measurement, right? When you do measurement, the family of possible outcomes is necessarily incompatible. You cannot have two and complete because you will have one. So, example, outcomes of measurements. So what is the mathematical correlate? It's what we call a PVM, a projection valued measure. PVM. Yeah, I write very badly, so if you can't read at some point, just raise your hand, please. PVM. What is a PVM? It's a family of orthogonal projector that form a resolution of the identity. Just as simple as this. So it's a family PFI such that sum over the PHI will be the identity. This is my notation for the identity. And they are mutually orthogonal, so PFI, PFJ will be, Kronecker delta plus the fact that they are orthogonal projectors, so Hermitian square to themselves. So this is what we call a PVM. But in the particular case, when all these projectors are one-dimensional, it's in fact an orthonormal basis. So in quantum information and a lot of contemporary quantum foundation, unfortunately we often do rigorous stuff in finite dimension, and we always struggle with the infinite dimension. For now, everything I've said is true in infinite dimension, but I will try to specify each time it's not true anymore. So when the FIs are one-dimensional, PVM is just an orthonormal basis. And in quantum mechanics, we never use bases which are not orthonormal. So very often, if I say basis, understand orthonormal basis. I will never say basis for something else, in fact. Good. Now, we can go further. So what is the mathematical correlate for physical observable? So of course, you know it's Hermitian operators, but why? Why is it so? Because when you have a physical observable, what you want to say is that it's a complete set of incompatible events, and you also want to associate to each event a real number, which will be the outcome of the measurement. So this is the reason why a basis plus basis labeled by real numbers turns out to be the set of Hermitian operators in H. But there is an explanation for why. Good. So physical observable are Hermitian operators. And now, last point, distinguishability of two events, or let's say two states. If you have perfect distinguishability correspond to orthogonality, because if you have two orthogonal events, then there exists a measurement, there exists an observable or a basis that you can probe, and with probability 1, you will get either one or the other, so you can distinguish them perfectly. Okay, enough for this section, and now let's go to the third one, entanglements. And density matrices. So I said to every system you associate a Hilbert space. Yeah, but what happens if I take two systems together and I consider them as one joint system? Which is a good Hilbert space to associate to them? Well, you all know that it's the tensor product, H1 tensor H2. Of course you know it, but let's investigate this, what it means and what are the consequences, and why we choose that as well. So the Hilbert space associated to S1 described by H1, so system S1, plus S2 described by H2 is H1 tensor H2. And I should be more precise. It's H1 tensor H2 equipped with the canonical extension of the scalar product, of course. But it seems obvious, but from an empirical, experimental perspective, it's amazing that the universe perfectly obeys the geometry, as the statistics of the universe perfectly obeys the statistics given by these rules in the complex, canonical complex geometry of a Hilbert space, plus its canonical extension to the tensor product. So is equipped with the canonical extension of the scalar product. So you know what is the extension scalar of should I write it? No, I guess no. I should? Yes? Okay. No, but it's, so scalar product of psi1 tensor psi2, phi1 tensor phi2 is the product. This is not canonical? Okay. Now, so we can give the definition of what is entanglement. Terribly simple. if so again we have this joint system S1 and S2. If the state of the joint system is psi, takes the form psi1 tensor psi2, so a pure tensor, we say the system is in a product state. Product states. And if else, otherwise, it is entangled, or the two systems are entangled. As simple as this. Yeah, notation. Very often we don't write the tensor product, so we write just this, or even just this, just to ease the notation. Now, of course, now there is a question you want to ask immediately. It's okay? I take the sum of these two systems I consider jointly, but of course, a question or an experiment I may perform on S1 only is also an experiment on S1 plus S2, and vice versa, right? So you want to say, okay, if I have the state, the quantum state of the joint system S1 plus S2, this state I should be able to derive from this quantum state another mathematical object pertaining to H1 only, giving all the statistical information of any experiment I could perform on S1. So I should be able to, to extract the statistical information of only S1 from a joint state. How should I do that? So minimal object. So what is the minimal object pertaining to H1 in H1 encoding all the information about S1 if S1 plus S2 is in a state psi. Right, so I should say an object that contains all the predictions. I should encoding all the predictions. So what is it? So I will give the formal definition, which in itself is not so often found, very detailed in most textbooks. But then later in this chapter, I will question much more what I will just assert now, because it's far from obvious, in fact, when you think about it. So what I claim that an event concerning S1 only is of the form, so remember subspaces, so it is of the form a subspace times H2. It's a subspace, right? So it's very natural with associated projector pi f tensor the identity on the second block. It seems very natural, but later we will question this more. But if you agree with that, then using the Born rule, we can compute the probability when being in state psi, joint state, of the event pertaining to H1. So again, it's this formula I love. Psi. Good, just the definition. I can rewrite it a bit more conveniently as this way. So it's a projector, so it squares as the identity. And so the modulus square norm is just the scalar with itself, so okay. And I can also rewrite it this way. So now you will start to wonder, why should I do that? Okay, cyclicity of the trace, good. And then, by definition, it will be, and this will be explained with the proposition below, it will be trace of something I call ρ1 pi f, where ρ1 is given by what follows, but where ρ1 is called partial trace, or let's say is the partial trace, denoted trace over 2 psi psi of psi, partial trace with respect to the second system, defined by the following proposition. So proposition so this proposition will be, so first I write it for finite dimensional Hilbert spaces, but in fact it will be true even in infinite dimension with a very small modification. So let H1 and H2 be finite dimensional. There exists a unique linear map that I call trace over 2, going from linear operator on the tensor product and outputting only a linear operator on H1, such that for all ρ1, for all ρ2, trace over 2 of a pure tensor will just be the trace of the second times the operator on the first. Unique linear map satisfying this. And it satisfies, in particular, satisfies for ρ1 2 in the tensor, for all A1 in H1, trace ρ1 2. So I write it just because I will need it at some point. But for fundamental purposes, we need it, but we don't use it every day. But this is this is true. And in fact, so yeah, I would just say it orally. This is the result holds in infinite dimension, but you just have to replace linear operator by trace class. So yeah, B1 of H, trace class operators. And so the fact that it holds, so this proof you can find it in the literature, but you have to really look for, and you almost never find it in the textbooks. The fact that it holds in infinite dimension, you find it nowhere, and you have so a member of my committee of my PhD thesis told me, yeah, you should mention that it's true in infinite dimension. I said, yeah, but I don't know if it's true. And in fact, it's not absolutely trivial. And he's quite an expert on these problems. And the only reference he could give me is in some obscure notes of a course of some guy, a mathematical physicist. So almost no one tries to check. But this is fundamentally fundamental to define the generalized Born rule that I will come to just now. So first, useful characterization of the partial trace, because, well, this is good for definition, but for actual computation, you will rather use this. But so what I'm about to write is used really in everyday life of the quantum physicist. So the trace over 2 of ρ1, 2, you want to know what are the coefficients, ij. So by definition, I can write it just to, to become familiar with Dirac's notation. I can write it this way, where, this would be the canonical basis or whatever. This is just definition of what are the Dirac notation, but the statement is this. Where EI and FK are basis of H1 and H2. Basis. So now I should be more precise. So when you ask for the coefficients of an operator, in fact it means the coefficient in a given basis. So here it means in the basis EI that I've chosen. In which space? So this is EI are basis of H1, and the FK is a basis of H2. And so when I fix the basis EI, I ask for the coefficients of this. It is given by this formula, and importantly, it doesn't depend on the choice of the FK. Not absolutely immediate here, but it's true. So this formula will hold because it's a trace. In fact, it's a sum over FK, so it's a trace. So you can have the intuition that it will not depend on the choice of FK. Okay, all right. So this is just for computations, but now, as a foundational. So, oh well. Yeah, I'm still not used because you have to pull quite strongly, but not too much. So now let's go back to foundational aspects. How do we use this proposition as a basis of the most general state for a physical system in quantum mechanics? So consequence, the most quantum state is in fact not psi in H. In fact, it's a rho. So I will explain this just now, called density matrix. So yeah, I will specify what this means. But so why? Because when you have a system, in fact, it may be entangled with another one, but you may not know. And so you have it, and you want to perform experiments on it. The results of the experiment you will obtain, if the system is entangled, will not be given by any psi and the Born rule I gave before, but it will be given by computing this Born rule, but on the projector on the big space. and no psi in a single H can account for the experimental outcomes that you will obtain if the system is entangled. However, there exists an object that specifies all the possible all the statistics that you will obtain in the experiment, because you can always trace out everything else. So in fact, the system, there exists maybe a big psi in the Hilbert space of the universe or whatever. You don't know the rest, but you know that if I trace out everything, I can obtain, there exists a row obtained by the partial trace that encodes all the possible results of probabilities that I can obtain. Now the question is, where does this row live? What is the mathematical nature of a partial trace of this kind? Well, one can show one can show that a row obtained as such a partial trace is a positive Hermitian and trace one operator. So we denote S of H this set, the set of all density matrices. The density matrix is a positive Hermitian trace one operator. And we have the generalized Born rule. I said generalized, but in fact it's the only Born rule. The other one was in fact a particular case. But now, how do you the most general way to compute probabilities in quantum theory? Probability of an event given that you are in state rho is trace of rho by f. So this is a little bit less wonderfully elegant than the first one, but it's still quite cute. And if so, in the particular case where rho is a rank 1 projector, we say that the system is in a pure state. If it's in a pure state, it means that everything that I presented first, before introducing the density matrices and so on, applies. So I can use the normal, the first Born rule and so on. But if you are not in a pure state, then you are set in a mixed state and you have to use this formalism. Otherwise, it is in a mixed state. Good. And you can check, of course, that the generalized Born rule reduces to the normal Born rule in the case of pure states, because trace psi by f. I just reverse the computation here, right? It's just psi by f psi, and so by f. So of course you reduce to the normal Born rule. Now let's go to Schrödinger equation. Yes. Yes.
When rho is a sum of
Yeah.
canonical products,
Yeah.
the state is separable and not
Exactly.
no.
No.
Mixed state.
Separable state is a convex sum of pure tensors. But the difference is that
you say that a mixed system is not entangled.
No.
When rho is
a mixed system is generally entangled.
You can have a sum of rho A and rho B. This system is not entangled.
It could happen, but most of the time it will not happen. But the definition I wrote is still valid. Entangled means, yeah. Honestly, I don't see the
you do not need to
why it's so important. But all right, I see what you mean. Okay, thank you. So now, so this was kinematics, and now let's go into dynamics. So the wonderful thing with Schrödinger equation is that it's almost tautological. There is almost no choice, but of course, almost hides a lot. But the key ingredient to see why you need Schrödinger equation and it cannot be another equation is Markovianity. So key ingredients, the laws of physics remain the same over time. The Markovianity. There's no clock. Should check myself. Right, good. The laws of physics remain the same over time. This is Markovianity. Isn't it the most basic requirement that you want to call something laws of physics, right? So it's not much of an assumption. Otherwise, yeah, you would probably use another expression than laws of physics, possibly. We can debate this, but now, more precisely, or not precisely, but the punchline is Schrödinger equation is basically the only Markovian time evolution that respects the structure of the Hilbert space. Okay, so this is the punchline, and now I'll be a little bit more precise and specify exactly the assumptions. So there are 4 assumptions, but none of them is terrible. They seem extremely natural when you do physics. So the first one is we want more precisely, we want for the evolution of pure states first, and then we will we want first, we want a family of maps, but I don't say they are linear or whatever, just a family of maps UT they are maps from H to H, indexed by a real parameter T. And because I want, you know, something that tells me if I'm in state psi after time t, I should be in state psi ut psi. I want Markovianity. Because I want Markovianity, I have a group structure. Yeah, maybe I could say I want a family of map UTT prime. Yeah, I should, yeah. Yeah, I should say that. I want a family of maps that if I'm in state psi at time t, what will be my state at time t prime? But because of Markovianity, in fact, I have a group structure ut t prime is in fact u0 t prime minus t, so I can just reduce to one parameter. And so the group structure is that ut plus t prime should be ut prime, because the laws of physics do not remember what happened in the past. So I just evolve and then evolve again. It's the same as if I had evolved the full time from the start. Good? No, not good. A question? No? Okay. Why? Yeah, I'm very interested because this is really personal. I've never found anywhere, almost everything from the start is really personal and not copied from a textbook. And so this is what I arrived at. If I'm missing something, please tell me. I'm very interested in this. C. We want that UT preserves the norm. Of course, because psi is supposed to be on the unit sphere. So I want the physical state to remain a physical state, so it should preserve the norm. But so now there is something, an assumption, popping out of nowhere, but it's what I said here, respecting the structure of the Hilbert space. We want UT to be a symmetry of the Hilbert space. So preserve the norm plus the scalar product. And magically, remind that I haven't made any assumption on continuity, even linearity, but magically, this implies that UT is a unitary operator. So linear, unitary. Well, is it so obvious? So Wigner showed it in 1931. Honestly, I've never checked the proof. I don't know how hard or easy it is. No. If you are unitary, you preserve the scalar product, but so Wigner showed it in the 30s. I don't know how hard it is. I think it's not terribly hard, but yeah. And last thing, but this is very reasonable. You want T to be strongly continuous. So you want it because you want to apply Stone's theorem, as you said, but you want it also because it's very reasonable to say that the evolution will map continuously states, and so that the probabilities do not suddenly jump. Feynman has showed that in fact you can also, if you have only weakly measurable, and I don't remember exactly what is weakly measurable, but it's sufficient. It's way weaker assumption. Therefore, so consequence, UT is a one parameter Lie group, and therefore by Stone's theorem, or so tricky thing, because you all know Stone's Feynman theorem, which is something on the representation of the Heisenberg algebra, but in fact Stone theorem has also been proved by Stone-Neumann under the weaker assumption, so we should also call it Stone-Feynman theorem, but then we are all lost. But by Stone theorem, then there exists H, an operator. So where is H? H is up. So no, first, yeah, H such that UT is the exponential of H. So there exists an infinitesimal generator of the one parameter Lie group. Where is H? H has to be in the Lie algebra of the unitary group. What is the Lie algebra of the unitary group? Is the Hermitian operator. Good. So I will make a comment just afterwards, because I'm thrilled. Like this is the reason. So one of the reasons that make me love quantum mechanics so much. This kind of miracles. Or equivalently, I can just rewrite this as I and you have it. Schrödinger equation. So this is wonderful. I still do not have an explanation. It could be a puzzle for next week if you have an idea. Isn't it a miracle that the Lie algebra of the unitary group is precisely the Hermitian operator, precisely the set which we can, because of the first section, which we can interpret as a physical observable. Because if it was anything else, then you cannot give a physical meaning as an observable to H. How come? I've nothing, no explanation. But if you have anything for next week, please tell me. For Dirac equation? Dirac equation is about fields, right? So it's already, the framework is completely different. You are already talking about bundles of operators of a manifold and so on. So in far from this. A bit like your observation before, you were already talking about Dirac spinors, so the structure is Pauli, yes, but we okay, yeah, okay. So enough for not enough for Schrödinger equation. So it's a Hermitian operator, great. So it could be perhaps a physically meaningful observable. Which one is it? So first, so physical meaning of H. Is there one? First, it's a conserved quantity. This is because D Well, I don't have to do the computation, but yeah, it's trivial. Good. What else? Well, first, this is Noether intuition. Noether says symmetries implies conserved quantities. And here, the symmetry is the constancy in time of the laws of physics. So there should be a conserved quantity through time. We have it. Symmetry here, constancy of the laws of physics, Markovianity, implies conserved quantities. Yeah, so we know from other fields of physics that the conserved quantity associated to time translation is energy. Yeah, but I'm supposed to be super fundamental here, so if I use other intuition from other parts of physics, it's a bit hand wavy. So for time, well, I should write it here. For time translation, we know it's the energy. But as I said, I'm not super happy with this. I remember. Good. Yeah, I was about to say this because I remember it was not in quantum mechanics, but in my first QFT course, the teacher was saying, "Oh, look, Noether charge, Noether conserved quantity, time translation. We call it the energy." I said, "Okay, good. How do you know that this operator is indeed what we are used to physically call the energy when I do an experiment in a lab and I have an apparatus to measure energy?" So, and he told me, "Oh, you can take it as a definition of the energy." Okay, good, but you can do that. But then you have to match everything you know about energy in all the other fields of physics, right? So you can indeed you can take it as the most fundamental definition of energy. Sorry? Yeah. So no, but with Noether, we are used to say that the Noether charge associated to time translation and the generator of time translation, we are used to say, yeah, it's the energy. But yeah, as you say, you could have something else. It's just a motivation. I'm just saying, yeah, this observable given by Stone theorem, you could say it's the most fundamental definition of what I call energy. And then you have to look back into even in classical physics and say, how come people in the 70s in the 18th century observed that there is something that is conserved all the time? Well, maybe it came from this in the very beginning. They didn't know, but there is something conserved, and so they observed that something was conserved through time, and they called it the energy. But no a posteriori, we see much better, and we know where it come from. But I agree, it's very hand wavy, and I'm not fully satisfied with this. So, any remarks you can have? I'm listening carefully because. No. Yeah, that's why I said Noether intuition. Yeah, but Noether theorem it's not what I use here, but Noether theorem gives you one particular observable, right? Yeah. And here it's yeah. Without making. Okay. No.
Because H can depend. Then have to be
True.
Well,
Well, this does not depend on time. Certainly not.
Yeah, but you are in very particular case.
Yeah, we are. For now, pure states. Then interactions, we're coming to it. But for now, isolated system, yes.
There is no contradiction. Pure states are.
No, but
dynamics.
If you want, this is the Hamiltonian of the universe. It doesn't depend on time. Yeah. I mean, no, but I mean, when you say H can depend on time.
Nothing changed. The principle is not this one. The principle is that unitary transformation are compatible with general unitary.
But yeah, this is
including this one. Do you not need to define any unitary transformation is compatible with? For example, if you take a photon and you make a polarizer, the polarization of the photon.
Yeah.
The Hilbert space of polarization is not described by any
Well, if you really model the details of the apparatus, I think you can. Yes, I think you can write a Hamiltonian. It would be terrible. No one would do that. But I think you can model with the Hamiltonian of the yeah. And I'm just motivating the Schrödinger equation. And I'm not. If you're right, I'm not using the true Noether theorem. I wrote Noether intuition. It's a bit the same intuition when I have conserve. So here the laws of physics conserve through time. It's not surprising that I have a conserved quantity, but indeed, not a Lagrangian formulation, not the true Noether theorem, but we recover the same patterns. And again, yeah, I'm just trying to motivate Schrödinger. And again, I believe fundamentally that as far as we know, the universe is Markovian. The laws of physics do not change over time. So when H depends on T, it's an artifact because at some point the experimentalist turns on the magnetic field or whatever. But if you model the experimentalist also in the setup, then the laws of physics are still the same, and the Lagrangian of the standard model is not supposed to change, one day or another, right? And so. This I can buy this, yes. Yeah, but don't you think that any UT, any transformation that you can make on a system, on a quantum systems, could, at least in principle, be modeled by a Hamiltonian of a bigger system in the non-relativistic case? Yeah, for now, yeah. For now, I did not, but good transition. Let's go for non-isolated. Yeah, true. Yeah. So, Yeah. Okay, let's be. Let me be even more provocative. Before. But now, I think you will disagree very strongly, and it will help me change my mind. Shouldn't we call Schrödinger equation Noether equation? Because so should. So please tell me I'm wrong. Should Schrödinger equation be called Noether equation? Why? Well, I'd like to write this. Noether tells you that the infinitesimal the conserved quantities are the infinitesimal generators of the symmetries. So Noether tells you this, and this is Schrödinger, right? Mu 1 2 3 4 0 1 2 3 time and yeah, and I take, and this is the p mu of QFT, right? And this is in the Fock space, right? So in fact, Schrödinger. So please tell me I'm wrong, but I've never seen this anywhere else in any books, and I had the idea one day, and I think it's wonderful, isn't it? So I don't know, but since you have nothing to say, I dare to box it. P mu is the operators given by Noether theorem. Now I'm reading QFT, right? So Noether tells you all the Lagrangian has a space-time translation symmetries. So Noether tells you that there are 4 operators conserved, and Noether also tells you that they are the generators of these symmetries. So by definition, Noether tells you. So in fact, isn't Noether equation the most fundamental theorem of all physics? I don't know. So yes, but you could if you want. So but then you just have the spin equation. Yeah. But this everyone knows. Whereas this, no one never said so. I said charges, but it's charges maybe when it's not an operator, or yeah. Do you agree with this? Charge operators for space-time translations. So yeah, I dared, and apparently you're not too shocked. So good. We have the same problem in QFT with the definition of H, because there are at least 3 ways to define H. So you could say it's the Noether charge associated to time translation, but you could say it's the generator itself of the time translation. Normally it should be the same. And another definition, it's the Legendre transform of the Lagrangian, whatever. Is it clear that it's the same? I don't think so. Maybe there is a difference when you are interacting or not, but we have several definitions of H and so energy. So we say, oh, the most fundamental definition of energy, okay, but you have at least 2. So yeah, it doesn't change anything, does it? I don't. Not for QFT people yet, but for us, not at all. Not at all. For us, it's just 2 absolutely equivalent.
The difficult point is the algebra.
What do you mean?
For example, for rotations, you must have
Yeah, the P mu commutes, right? And
for rotation.
Sure. And what's your point? Yes.
My point is that you cannot use the commutation relation from
No, but we start with the symmetries. We start with the symmetries. Okay, back to quantum mechanics. For mixed states, Now I'll just give you the formula because it's just not interesting to derive it, but it's very obvious. If the system evolves on its own, so yeah, is isolated, no coupling with other surrounding systems, the evolution will be rho become ut rho ut dagger. So this is very natural because rho for pure state it's psi, you know, so you want to evolve both sides. It's a 2-0 tensor, so, or 1-1 tensor, so of course you want this. And then the equation becomes what? A 1-1 tensor, no? Yeah, because rho, look, for pure states, rho for pure state it's of this form. So when you evolve, you want to act by ut on both sides. And so here you have a dagger to okay. Should I write it or good? Okay. Or equivalently, so this is the Schrödinger equation for density matrices. So just because now we have a 1-1 tensor, so this is the Lie derivative or whatever. And I just mentioned briefly, but I don't do it in my course because this you can find in literally every textbook. How do we build the other physically meaningful observables? So first, there are literally only 4 physically meaningful observables or functions thereof, but no one has never used, I think, anything else than h, x, p, and s. That's all, right? So there are way too spin, yeah, or the spins operator, and you could say and composition thereof, so angular momentum and so on. But so there are way too many observables, supposedly observable in Hermitian. No, certainly no. The Hermitian operators is a very big space, and it's not exhausted by just. Is it true? I'm very skeptical, but if it's true, please tell me. I would be great. Yes. Observables. So it's a fiction when you write Hermitian, unless you're right, but otherwise it's a fiction to write Hermitian operator and say these are the physical observables. You could name them the mathematical observable if you want, but the physical observables you have just x, p, and s, and functions thereof, and so they are built as you know, generators of physical symmetries. Yes, because x is a translation in phase space. Yes, translation in phase space and rotation. Yeah. In QFT, yes, but in quantum, yeah, but it's just written in terms of x and p, right? So I don't think in quantum mechanics harmonic oscillator n is a dagger a, and a is x plus s plus ip over, yeah. So just function of x and p. There is nothing else as far as I know. So yeah, phase-space translation, rotations. Good. Now we'll do something more quantum info oriented. CPTP maps. CPTP maps. Okay. Just to know how much people know what is a CPTP map, or at least know yeah the definition, just to know to adapt to the audience. Can you raise your completely positive, completely no positive trace preserving map? Okay, so but I know there are people who know, so please raise your hand for the people who really know what is CPTP. You do? No? Okay. Yeah. People who know, please raise it, just so that I add them to the audience. Okay, 3 people. Yeah, 4. You are very shy, but okay. Good. So we started with pure states. Then we said, oh, it could be entangled, and then we said, oh, we can derive the the mathematical object that contains all the information about only one. And but there is something else. We have said there is a time evolution. So we want to know what is the time evolution for only one system when it's coupled. So what is it? Well, if global unitary evolution takes place in H1 tensor H2, what is the evolution in H1 only? Restricted to H1. So it's very easy. You start with this. For the simplicity, let's say it's non-entangled first. And then you get this, where the U are unitaries on the tensor product. So now what is the map from density matrices in H1 to density matrices in H1? This entails a map taking rho and outputting the partial choice of this. U right, and so this is the most general quantum evolution. Now, sorry, row 1, row 1. Yeah, so 2 ways. First, you could require that it's linear. So by linearity, you can restrict to the pure tensors and then do the rest by linearity. Or maybe you start with row 1, 2. You compute the partial trace before evolution. You call it row 1. You apply the evolution. You compute the partial trace. You call this, and this is the CPTP. I will name it just now. So one can study the properties of the map psi. So there are 2 properties, two and a half. First property, one can check that psi is trace preserving. And one can check that it's a positive map. I should say non-negative probably. Meaning that if you have a positive row, psi rho is positive as well. And I mean, it was written here already because I said that psi is mapping to S of H. And in fact, so that's why I said 2.5, because in fact, completely positive. That is psi tensor identity is positive for all integer n, where identity n is the identity on Cn. Hn equals Cn. So I can extend my Hilbert space as much as I wish, and if I just act as the identity on the extension, should be also positive. So this is very natural because you need the trace of rho is 1 for conservation of probabilities. This is also very natural because you want the probabilities to be always positive, non-negative. And this, honestly, I have never found nowhere, but maybe I just should think a bit more about this, but I have more interesting to do. Why should we require that? Why should we expect this? Honestly, I don't know. So what I just, for now, I just said such a map satisfies this property. And I will also say just below that every map that satisfies this 3 or these 2 can be obtained as something like this, where you extend the Hilbert space, you act unitarily, and you partial trace. I'll just write this. But what is the physical motivation or the physical meaning of this? Honestly, for now, I don't know very well. Maybe someone in the room.
Imagine, okay, I have this channel acting on this specific states here, and now I imagine that I enlarge my space, so I'm considering actually a space. But since I know that my map was acting only on the space A, I will just compose it with identity channel on my right, because it's doing nothing. So I have something that is acting here. On the environment is doing nothing on the rest of the system.
Yeah.
Just this now, if I feed the map an entangled state, I don't ask for computing bigger map where I just compose the identity will send a quantum state to something that is not a quantum state, in the sense that I will look.
Yeah. Is it sufficient then? Because you would like to have not only identity but anything.
Yes, but identity is already something.
I think it's related to the Choi representation.
It is, but I would say the opposite. I would say Choi is the consequence of this observation. So a map satisfying these properties is called a CPTP map, completely positive trace preserving map, or in quantum info jargon, a channel. Channel because, yeah, input, output. Yeah, trace preserving. Yeah.
Yes, but this condition related to the.
Yeah, that's what I wrote, right? If you satisfy this, you can be called a channel. Am I wrong?
No, you need the complete. The map must be complete. Some of the terms of operator.
So are you talking about POVMs or something? Because I'm coming to this, and for me, a channel is a synonym of CPTP map. But perhaps I'm wrong. But it's a synonym, right? It's yeah. Okay. So if you agree on this, we okay. Now by a result called Stein-Spring theorem. It turns out that any CPTP map can be obtained as, in fact, extending the space and unitary evolution in the extended space, but tracing out. So how do I write this? The converse is true. Any CPTP map in H1 can be obtained as a partial trace of a unitary evolution on a larger space. Okay, Stein-Spring's theorem. And now, a little word about a very important result in quantum info theory, and a little bit of history also about this result. I've been working on this quite a lot. Something called the no communication theorem. It will bring us to philosophical remarks about the foundations of quantum mechanics. But first, let's do first historical remark. So in chapter 4, we will study Bell theorem, but you know at least that Bell theorem is about some kind of non-locality. And in the aftermath of Bell theorem, so in the 70s, 80s, there have been a revival of hope or craziness, maybe, of people saying that perhaps we can send signal faster than light using intelligently entangled particles. It was not so crazy, maybe, because yeah, this is the intuition behind Bell theorem. So after Bell, revival of hopes to use entangled pairs, to use entanglement to convey info faster than light. I guess everyone knows this. Okay. Hopes revive. And at some point, some people wanted to put an end to this and say, no, please don't be absurd. Quantum mechanics does not violate relativity theory. But so 3 guys that we will meet again in the measurement problem chapter for something completely different from the Italian school of the 70s, 80s. There was a fantastic Italian school in this era working on foundations of quantum mechanics. There's much to say also politically. I love to tell this story, but I don't have time. Maybe around the coffee later. Proved 1980. I thought it was 86. Well, okay. Proved for the first time, a no communication theorem. So in a punchline, an entangled pair cannot be used to convey information. Not only faster than light, you cannot convey information at all. Many other proofs followed, and I will come back to this in a moment. There are dozens of proofs. So let's state the theorem, or at least my version, which I think is the most general you can have. I will, and one you can find in contemporary quantum info textbooks. But yeah, I will explain maybe half a time what did they do and what did most people do before the quantum info era. Idea. So now we do quantum info, so H1 and H2 will become HA and HB for Alice and Bob, because Alice tries to send a signal to Bob. So whatever happens on to Alice's system, SA, does not affect the empirical statistics of Bob systems, SB. So what can happen to Alice's system? What is the most general quantum evolution? So you have SA, it's entangled with SB, right? Here is Bob, here's Alice. Okay, and what can she do? The only thing she can do is, you know, use another system and do a joint unitary evolution with SE for environment, and they can evolve jointly. So let's let the shared entangled pair be in state rho HA tensor HB. And recall that the most general evolution that Alice can do using an ancillary system, most operation that Alice can do but she can do a CPTP map, but only locally. So rho will be mapped to psi tensor nothing of rho, where this is a CPTP map. Good. Now let's write the condition of no signaling, of no communication. So we just write the probabilities that Bob will observe if Alice does nothing, and Bob measures anything he wants. And then we write also the probabilities that Bob will observe if he measures the same thing, but Alice has done something, has acted with the CPTP map. So probability for Bob For Bob, to obtain an outcome K, if Alice does nothing, so it's just the Born rule, right? But by K. But again, this is a question only on the system of Bob, so it's identity tensor pi K. I promised I will philosophically think about that. It's coming in a few minutes. I hope it's for today. Yes, probably. Then proba. So blah 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 blah. If Alice acts with psi, well, it's the Born rule, but just the row has changed. So, and then the same, right? And now, theorem, or I don't dare to call it a theorem because you will see it's not much. So proposition, but this is the no communication theorem. So yeah, no com theorem. For all row. Where? Here? Yeah, it's the identity on this on the B Hilbert space, because now I changed.
The operator is.
So rho is in here. It's the state of the entangled pair that they share. Very simple. This equals this. No communication theorem. So it's not only that they can't signal faster than light, because there is no notion of frame, there's no notion of speed of light in quantum mechanics, but you don't need it because you cannot convey information at all. So Bell non-locality, we will study this later, but it's more subtle because it's non-local, but in a very restrictive way. And so let's go for the proof. It's very instructive. So this proof is, so little advertisement, it comes from, I have one paper about QFT for the QFT people here if you are interested. First, I studied some, in an axiomatic way, some logical relationships between no signaling, weaker version of no signaling when you restrict to measurements instead of doing anything here, and also the fact that the unitary operation evolution operator is purely factorized. In fact, these three conditions are equivalent in quantum mechanics, and then I translate this the best possible way in QFT in the Fock space, and I showed that this implies that no signaling when measurements are understood in a pointwise way. So it's not very, we know there are a lot of problems in QFT because of this, but at least in this simplistic case, no signaling implies macrocausality, which gives a justification, motivation for the macrocausality axiom, which is kind of lacking in most textbooks because they just say, oh, measurements should not influence themselves. Yeah, but I mean, there is something to do, and there is some kind of work like this to do. And second, I show also that not only it implies macrocausality, but also you can derive the spin statistic theorem, the fact that fermion, spin and 1/2 are fermions and spin integer are bosons, because in the QFT textbook they say, oh look, so macrocausality is just because measurement should not influence at space like distance. Okay, and you have a commutator, but how do you explain that for fermions it's an anti-commutator, right? So you have some work to do, and yeah, so you can. This proof is from this paper. So bilinearity. Enough to show it for pure tensor, so rho equal rho A tensor rho B. And then you will see how tautological it is. Trace so a trace of a something tensor something is just the product of the trace. Right? Because you know you then psi is trace preserving. And then a reverse. And that's all, nothing more. The first proofs were much more complicated, and there were even, and it's crazy because they were more complicated. Even me myself, when I studied my PhD, I was annoyed with this compatibility between relativity and quantum mechanics. And I first showed the condition not for the CPTP map, but just for Alice doing a measurement, because I was annoyed with the measurement problem considerations. And in fact, Girardi, Rimini, Weber first showed the communication theorem for Alice doing a measurement and not anything. And in fact, not only them, but most of them until the 2000s and until the advent of quantum info attitude, everyone showed no communication for Alice doing a measurement. But why? I mean, Alice can do many other stuff, right? And why? Because everyone was so focused, just like me, for in the beginning with, I don't know, a special role of measurements in communicating faster than light, because the collapse is supposed to go immediately and so on. But in fact, this is, and it's crazy because when you do it for measurement, it's much it's not super hard, but it's longer. It's you have 6 lines maybe, and you have to work a little bit because you have to translate the fact that you are trace preserving, but for the measurement it's not that obvious, so you have to manipulate the sums and so on. Good. So I will finish with a philosophical remark. Which will allow me to be again very provocative against QFT. So Kennedy in 1995 published a paper I love. It's super simple, but it's I mean useful. It's when philosophers are very useful to physicists, I think. He showed, that means many times, all the time, showed that first, so all no communication proofs are one and the same proof. They're all the same disguised version of exactly the same proof. Sorry. One and the same proof, disguised version of the same arguments. 2, circular. They are empty, and it's not surprised when you see how tautological it is here. Why is it circular? Because no signaling was tacitly assumed in the very construction of the tensor product structure by von Neumann in 1932 in the reference book that literally everyone followed then, and no one never questioned again, almost no one, the why should, you remember in the beginning of the course, why should the Hilbert space for 2 systems be H1 tensor A2? No one questioned this except very few particular case that I will perhaps mention, but tacitly assumed by von Neumann. So I will explain a bit the argument of Kennedy by von Neumann in the very of the tensor product structure So here again an acronym that we use a lot, TPS, tensor product structure in quantum foundation. Why? So here's the Kennedy's argument, or not. It's not. Yeah, it's an argument, but it's Kennedy's studying precisely how Feynman builds the TPS and how everyone follows. So first, yeah, most textbooks just simply follow von Neumann and they don't even question why H1 tensor A2 is the good Hilbert space for S1 plus S2, but also everything that comes, all the machinery that comes together, meaning why projector tensor identity would be the good projector for the question asked to S1 only and asking no question to S2, and all the things that come together. So everyone follows von Neumann. Now, Kennedy's arguments. So yeah, I don't have time to write everything. I will write just the most important, but I would say already a lot of things now. Von Neumann derived the fact that we need H1 tensor H2 from other physical assumption, but always often tacit physical assumption. In particular, Kennedy notes that there is an universality assumption. All systems are quantum systems. Okay, good. Second, a kinematical independence assumption, meaning that when you have a combination of two systems, no new degrees of freedom appear, no incompatible subsystem states appear, and so it means for von Neumann, obviously, quote, obviously, the good Hilbert space is H1 tensor H2. So for H1 tensor H2, von Neumann claims, obviously, that no, for S1 plus S2, that the good Hilbert space is H1 should have basis, should have basis when I and J counts all the possible states for S1 and S2 in some basis, because there is kinematical independence, so all combinations should be possible. Therefore, obviously, but now there is something else. There is also an assumption of how do we extend the observables. So a physical observable of S1, sorry, the obviously was on this, but whatever. So a physical observable of S1 is obviously also one in S1 plus S2. And the extension is tensor identity. So A1 Hermitian in H1 extends obviously as A1 tensor identity 2. And the only justification he gives, it's not so bad. He says, well, you want that, the square of the extension is the extension of the square, right? So consistent with functional dependence. So this is satisfying, but is it necessarily conclusive, right? So this is the only justification given by von Neumann. And now, last thing, coming to no signaling, it's harder and harder. Coming to no signaling, von Neumann requires something he calls an invariant condition. He wants to say that the probabilities, if I compute probabilities on the smaller system, it should be lead the same prediction as probabilities on the bigger system. So of the prediction. So I do it really short, but trace rho1 A1 should be equal to trace rho A1 tensor identity. This is very natural, and we started by this when I defined the density matrices, so it's very normal. But this implies that rho1 I equals sum over j of rho ij ij. And in terms of probabilities, what is it? The diagonal elements of rho I in some basis. It's just the probabilities of having outcome I. You can check with the Born rule. So this is probability of I will write something here. Is the sum of the Pij. But it's the probability of having I. What's the difference? Well, here you just consider S1 and you don't even consider the existence of S2. So I, knowing that doing nothing on S2, and here, well, you do a joint measurement and you just consider all the possible and sum all the possible. You do a marginal on all the possible outcomes of A2. So measuring S2, but this is precisely the no signaling condition. This is the no signaling condition. So if you want to remember only one thing of Kennedy's paper, the punchline is first that all the no signaling proofs are circular because, in fact, no signaling is deeply rooted in the very building of quantum mechanics. But second, and for me, it's for quantum foundation and also quantum gravity, and also QFT, the foundation of QFT, it's crucial. The TPS, tensor product structure, encodes the quantum mechanical notion of locality. The quantum mechanical notion of locality is nowhere else to be found else than in the TPS. Whereas, and I think this is the deepest difference, the deepest conceptual change. So I claim something a bit bold, but I really think that. I think the deepest conceptual change between QM and QFT lies in the loss of the tensor product structure. And so in QFT, the notion of locality, the TPS, is replaced by algebras of observable over a background space-time manifold. So it's very useful to implement the Lorentz symmetry or whatever, but doesn't this mean that quantum mechanics is a more promising route for quantum gravity? Because you don't have, the notion of locality exists, but it's not implemented in terms of a background space-time manifold, which is what dooms the QFT attempts to reach quantum gravity. Because the biggest lesson of, I argue again, of general relativity is the fact that there is no background. There is the fact that quantum the matter and space-time co-create themselves, they co-emerge. And so if I should summarize the challenge of quantum gravity in one sentence, I would say, well, there will be many such sentences in the course, but the first one I say today is the challenge of quantum gravity is to build a backgroundless theory for quantum matter. But quantum mechanics is backgroundless and still has this notion of locality. QFT cannot have, because in the very essence of QFT, you have this background manifold. And you can curve it as much as you wish, it's not dynamical. So, yeah, last remark for today. Sorry for being a bit late. No, it's not. What I said about local, yeah. I will write the TPS is what encodes. So first here, nothing. Yeah, but you understood. It means the conclusion is that the proofs are circular because it's already present in the very building of quantum mechanics. Okay, this I guess I think you get it. But now the conclusion is TPS is what encodes the quantum mechanical notion of locality. Deepest change. So my claim. I will write I because really don't take it as a textbook thing. Nothing was, but this particularly not. I claim that the deepest change between QM and QFT is the loss of the TPS. In QFT, it is replaced. The notion of locality is implemented by algebras of operators on a background spacetime manifold. Okay, and so yeah, so it was in a nutshell, is quantum mechanics a more promising route to quantum gravity than QFT? Because it has everything you need. It has a notion of locality, but by the way, it's a much more operational notion of locality because contrary to QFT, where the notion of locality is based on a manifold, where you have billions, an uncountable number of events that in fact refer to literally nothing because most of the points on the manifold, nothing happens, or you cannot even refer to them. Contrary-wise, in quantum mechanics, the notion of locality is very operational because they are between systems. The TPS says that there is a locality between actual systems on which you can experiment. You know exactly what you're talking about. And perhaps the reason, I think it's not my claim, I think this is quite uncontroversial, maybe it's not. One of the possible reasons for having so many divergences in QFT and the need for renormalization and so on is possibly due to the fact that you have way too many points in your space. And that's why so many people try to discretize spacetime and so on. And in fact, they get rid of the divergences, but they have other problems, of course. But so in quantum mechanics, you have much less points because your points are actual system, operational system, not fictions, because the spacetime manifold is from the very start a fiction, and that's why quantum QFT is so ugly. Well, I love it for other reasons, but it's very hand wavy. So yeah, is quantum mechanics a more promising route? Because yeah, so this I said it. The challenge, what is quantum gravity? The challenge to build a backgroundless theory for quantum matter. Einstein managed to do this feat more than a century ago for classical matter. In a century, no one never managed to do this for quantum matter, and I will explain in the next chapter why it's so hard. What is the property of quantum matter? In fact, it's the measurement problem that makes it so hard. But yeah, okay. Last, if you allow me 2 more minutes, just one, but very, very short. The tensor product. So if you meet a mathematician and you say, well, I'm working on tensor product, the mathematician will say, okay, you are brave, because this is a super hard, super complicated mathematical object. It's very mysterious. You have a crazily easy or natural definition. You can't imagine a more natural thing, and yet everything is an open question. And there is a paper, I like the title, by Hiller and Lim, most tensor problems are NP hard. For example, so tensor products, super deep math notion. 𝗦𝘂𝗺𝗺 and 𝗦𝘂𝗺𝗺 title of the paper, most tensor problems are NP hard. Example, if in quantum mechanics, there is very simple illustration. Determining whether psi in H1 tensor H2 is a pure tensor, meaning a product state, meaning a non-entangled state. Is NP hard? Yeah, a question? Yeah. You can't read?
Complexity class of the meaning
for yeah, so maybe people here are much more aware than me on this. It's you know, for in computing science, problem that cannot be solved in polynomial times, but I don't know more or barely more. But
can be verified.
But yeah, it can't be. Yeah, that's it. So just remember that there is no simple and efficient algorithm. If you input a state in the product Hilbert space, there's no efficient algorithm to tell you yes or no. There exists psi1 and psi2 such that it's a product state, meaning there is no simple algorithm to tell you if there is an entanglement or not, because there are so many ways to rearrange a tensor product state that it's really not easy to factorize it. It's much harder than factorizing a normal product because yeah.
Even if you develop psi on the tensor basis, then you have a relation.
Yeah, but the relation grows exponentially with the size. NP hard always means asymptotically in the complexity of the problem. So in the for two-dimensional for two-dimensional you compute the determinant and you're done. But then you can write we could do it. It's very easy. You write the condition, yeah, but there are so many cross products that at some point it's crazy. Why do I say this? This is the reason why entanglement is so hard. And this is the reason why there are so many difficult open questions in quantum info. And this is the reason why so many papers continue to appear. It started about approximately in the 2000s, and we are far from having even thought of all the questions you can ask about entanglement. And it's finite dimensional problems, but it's terrible. So I stop here for today. And yeah.